In the previous section, we described different FPGA I/O data types. By the end of this module, you will be able to scale RSeries analog I/O by using integer math. Okay, let's talk about using integer math with analog input and analog output. So with RSeries cards, a lot of times what will happen with analog input is it'll convert a binary representation of the voltage to a signed integer. So for example, the analog input would be reading a voltage. Maybe it's going from negative 10 volts to 10 volts. And then in the FPGA, it makes it into a binary representation of that. And if the FPGA hardware for that is analog input with a 16-bit resolution, then it's going to use 2 to the 16 bits to represent that voltage. So at that point, you have a binary number that has 16 bits of representation that is representing that voltage. What you can do to get that back into engineering units, one way you can do this is you can pass this raw unscaled binary data to the host VI for conversion to volts or other units. On the opposite end, with analog output, you could start in the host VI, and then you can take an engineering unit of volts and then change it into a 16-bit binary representation. And then you can write that binary representation of the voltage to the D to A converter of the analog output. So let's take a look at the numeric palette. So a lot of the basic numeric functions on the FPGA target are still available to you. So you have addition, subtraction, and things like that. Let's talk about integer division. So if you're taking a divide function and you have two integers going into that divide function, then it's not going to return an integer value. It's actually going to return a double precision floating point value, which is not supported on FPGA. So you must use other functions for integer math. So one way you can do it is you can use the scale by power of 2, which we've talked about before, if you're dividing by a number that's a power of 2, like 4. Or you can also use the quotient and remainder function. And that one is going to do the job, but it's going to take a lot more FPGA resources. So in this slide, we have an example of doing some scaling with RSeries in LabVIEW FPGA. So let's say we have an output coming out of that I/O node. So we're reading an analog input channel 0. And really what we want to do is we want to scale that by a factor of 0.7. So one thing we can do is we can try to get something close to multiplying it by 0.7 by multiplying it using integer values. So we can use a scaling factor here of 11500, and we can divide it by 2 to the 14th. And if you do that math, then what you actually get is 0.7019, which is a value that's very close to 0.7. So you can see in this example, we were able to multiply the value of analog input channel 0 by 0.7 using integers. So we were able to multiply by an integer and do a bit shift kind of function with the multiply by a power of 2 function to get something close to 0.7. So as I stated earlier, the RSeries FPGA I/O node with analog values, it's going to return a binary representation of the voltage input. So for example, over here, we've got something with a 16-bit resolution on our analog input channel. So if you look at the bottom, we've got 0 going all the way to 65,536. These values are representing a voltage, but we're seeing the full resolution there. So if we wanted to convert this number, so if we want to convert 0 to 65,000 into something like engineering units, for example, negative 10 volts to 10 volts, then we would need to do some sort of conversion. So you can either do this conversion on the FPGA VI, or you could also send it to the host and have the host handle converting that binary representation into an engineering value. So conversion to binary representation is hardware dependent. Each hardware target's going to have its own specific voltage range. It's also going to have analog to digital conversion precision. There's going to be offset and auto zero values as well. By looking at the help documentation for the device you're using, you can use these hardware-specific values and use the values for conversion of the binary data on the host. So at this point, it would be good to do exercise 4.1. In exercise 4.1, we're going to take a look at RSeries IO. So what you'll do is you'll create a project, have an RSeries FPGA target there, and you're going to add IO to it. Then you're going to create a VI that uses that IO, and then you're going to simulate the execution by executing the VI on a development computer. And then when you run it, you're going to get simulated values of that I/O. So you're going to see simulated digital data and also simulated analog data. Now you can scale RSeries analog I/O by using integer math. Next, we will describe the data type, module properties, and module methods associated with compact RIO I/O.